Our last lecture will concentrate on a theme which is important to research, for materials research, and I have worked on this for a number of years, and I still work on this, and it's quite multidisciplinary because it involves natural fibers, therefore plants, fibers from plants or from animals, in the sense that, for example, there have been also materials developed from wool, and wool is from animals, of course. And basically, what the idea is that you try to work on the substitution of the so-called reinforcement for composites, which can be in carbon fibers, glass fibers, basalt fibers, Kevlar fibers, but most part of the market is fiberglass, therefore the reinforcement with glass fibers. The problem there is that glass comes from silica, and in general terms it's a natural material, but at end of the end of the day, at the end of life, it's poorly recyclable. So there have been a number of attempts to put some other fibers instead of glass fibers, or in combination with glass fibers. So you produce hybrids. We say hybrids in this particular field when we are introducing two, in some cases even three different fibers, some of which may be natural fibers, others might be synthetic fibers like carbon or glass and so on. Of course, there is a question of which fiber you want to use. So a kind of selection. And here it's a complex matter because in practical terms, there are a number of natural fibers around the world, and we are fair if we say that every country has got its traditional natural fibers. And then, of course, you want to have some properties which don't need to be superior to fiberglass, because you have a material which is inherently more environmentally friendly, with a number of caveats, with a number of observations you need to make. It's not just because you use natural fibers that the material is more environmentally friendly, because then you put these natural fibers into a matrix, which can be a thermoplastic matrix or a thermosetting matrix. Plus, you treat the fibers in some ways, in most cases. Treating means that you have some chemicals which are supposed to increase the hardness of these fibers. Like, for example, sodium hydroxide is a typical example. Or you are supposed to bleach, so make whiter and more regular the fibers, like with sodium hypochlorite, but you may have a number of different chemicals used in them. We may discuss a few of them later on. Of course, there is always a kind of emphasis on the fact that we could use waste. We could use waste for productive systems. For example, from hemp, we are trying to reintroduce hemp in Italy, also in the Marche region. And hemp is used for textiles. It might be used into bioplastics to make materials, materials in the form of films. Or we can have, of course, a food related uses like for oil, like for seeds, etc. Therefore, we may have waste from this productive system, and we may think, why not using them also to material. Here below I've shown two examples, coconut fibers, which is called coir, um, which is a part of a large productive system, because from coconuts, basically you take as for fibers, the seed air, which are taken from your fruit, basically from the skin of your fruit. And in other cases, for example, here in the Amazonia, we have these fibers which are called guaruman, which are example of a typical local fiber. The first thing you do, usually you put them into epoxy because it's easy, and you can see that the properties change. So you have some epoxy, and then you add some amounts of these kind of fibers. This is an example. And we can say that it's a part of a productive system. And in practice, we have most applications are for textiles. And so these are some examples. Coir fiber is used in geotextiles, for example. And geotextiles are textiles which are used for operations performed on soil, so to be able to maintain the soil and not to allow sliding. Then you have a number of other possibilities, and of course you have a number of other possibilities also in terms of textiles. You can have a kind of flexibility in order to take a number of different textile geometries and fiber orientation and so on, which is what is usually done also in glass fiber. Glass fibers, you can insert them into different geometries and also laying them up in order to have this kind of sort of orthotropic material, not an isotropic, but an orthotropic material, which at least in every direction has got constant properties. So the choice in terms of fibers is very wide. This is an example of a few fibers. There are many more. If you look into literature, you can see that a number of fibers are present, some of which are more successful, others are less successful. Some of which have got a large productive system, like it is the case for hemp, for example, for bamboo. You can do any kind of products from bamboo. In other cases, there is a leading product, like it is the case for banana. You have a leading product. Most banana trees are cultivated, I would say 99% banana trees are cultivated in order to produce the fruits, and the fruits are sold. Beyond that, you have some waste, which might be the leaves, because you have to prune the trees, so to have a kind of maintenance of the tree. And you have other kind of waste, which is also of interest now, like banana peels as well, are a waste which might be collected, less easy to collect than the leaves from pruning, but still a waste which can be used. And then a number of other possible crops, possible from which you can take fibers. Then you want to make fiber matrix composites, and the problems are always the same. You want to impregnate them with a polymer matrix, so in practical terms, what you want to have is that they are wetted with the resin in a uniform way, and that you are able to insert the maximal amount of fibers which you can put, because you put fibers in order to have tensile strength, and you want to insert them the maximum possible amount in a 2D or possibly even in a 3D geometry. You can have also stitches in order to keep the laminate together also in the 3D dimension. Then you need to study the polymer rheology. We have studied already, we have talked already about the rheology, so the way that the polymer flows and the way that the polymer is able to impregnate those fibers. So we have these kind of fibers. The fibers can be treated, for example, with alkali, with sodium hydroxide. This is again coir, which is treated with alkali, therefore sodium hydroxide in most cases, which produces some voids, some porosity, some reduces the irregularity, but you don't get a very regular fiber like it was the case for glass, carbon, Kevlar, basalt. You get something which is irregular because it comes from a plant, because it has some limitations of lengths. You could imagine to do like here you have a rope and you can imagine to have even 1 kilometer long wire with basalt, for example, with carbon. Even with carbon, you can have some kind of rods and rovings, etc. And you can buy them like that and then cut them or manage them in some ways in producing fabrics and so on. With natural fibers, with plant fibers, the situation is not the same because you are limited to the dimension of the plant. For example, in hemp, the fibers you are able to get are around 1 meter long if you are lucky. With bamboo, you can get fibers much longer than that, but anyway, you have a limitation. The only natural fiber which has got a very considerable length is silk. With silk, you can have even 600, 800 meters of fibers in just one cocoon. And when you unwrap that cocoon, you get that very long wire, which is good in terms of flexibility. In plant fibers composite, if you start as an engineer, so you have a polymer matrix, you have the natural fibers, and you want the compatibility, you want they bond, they are bonded in some way, these polymeric matrices and natural fibers. Which is not obvious because polymeric matrices, in most cases, the traditional polymeric matrices, say polyethylene as a thermoplastic or polypropylene or epoxy as a thermoset, they are hydrophobic. A plant fiber is hydrophilic, more or less hydrophilic, but still hydrophilic because water needs to circulate across the plant, so it is hydrophilic. So the compatibility is not ensured. That's why you treat the fibers. Of course, there are a number of aspects which we are not very happy with. You can examine the environmental aspect. You can have a life cycle analysis, so to analyze the environmental impact of the substitution of glass fibers with the natural fibers, say glass fiber with flax fiber or with hemp fiber. You want to examine the environmental aspect to see whether this substitution is more or less environmentally friendly than initial situation, fiberglass, say. Then you want to study the dynamic properties, the impact properties. I would like to spend some time here to talk you a bit of impact properties of materials, which is important as well. Fatigue, you know already, and fatigue is fatigue testing is performed a lot also on composite. So you have this kind of cycling. And of course, you want to build a database. The literature basically builds a database with data which sometimes collide between each other because we may have a variability. Every time you approach natural materials, you are faced with a large variability. Large variability means that, for example, from different plants, coming from different regions, or even from the same plant, the fibers from the same plant may have a large variability, which is a problem because you have to set your design to the lower value, the lowest value of your range, which is a problem. For example, here you can see one problem which is important if you want to make models. For example, we have AMP threads. Consider that usually the fiber is made of threads which are subjected to a torque, and basically they are put together by a torsion force, by a kind of torque. And to do that in an effective way, we would need to have some cylindrical threads. If we have cylindrical threads, then everything is easier because we are able to place in the same space, in the same area, we are able to place more fibers. Therefore, the material is going to be stronger, at least in tension. And this is what happens with fiberglass, with glass fibers. This is not what happens with AMP fiber, which is one of the best, which is one of the closer to the cylindrical geometry. Plus, there is another problem. They are not cylindrical. Also, they need to have water passing. So, inside, they have porosity. They are not filled inside, completely filled. I'll show that later on. Some examples of fiber treatment. We can treat them aggressively with, this is what was usually done in textiles. So the treatment with alkali, like sodium hydroxide, or bleaching, which not only makes them more regular, but by matter transportation basically, but it makes them also somehow whiter. Then we have other treatments with sodium sulfate, which reduces the fibrillation. What does fibrillation mean? Fibrillation means that the fibers are put together with torque into the filaments, the fibrils are put in a larger fiber, in a technical fiber. We refer as to technical fiber to the fiber which we are able to work with. So we are able to do fabric with technical fibers. Although the fiber, the plant is much smaller, but we put them together with the torque, and then we are able to have the technical fiber. Once we apply the load, what can happen is that the fiber tends to separate from each other, so we have this kind of fibrillation. So the fibrils come out again. Which is if you have an idea of textiles, especially natural textiles, you have with wool, it's very evident, but also with cotton, you have this kind of fibrillation. As a matter of time, the fibers tend to come out. This happens also with synthetic fabrics like polyester. Then we have the typical treatment for fiberglass, which is silane, which we can coat fibers. We can have some natural substitute for silane, which is, for example, shellac. Was a typical, was one of the protoplastics, was made with shellac, and which is natural substance. Um, and what can what can we do as well? We can, for example, with acetic acid by acetylation, can have the same effect, although much diluted with citric acid, so acid from lemon, and we can better moisture control, and they become also harder. They tend to become even a little bit more um, resistant to temperature, because there is another effect which we need to consider, is that plant fibers don't get to the same temperature we were accustomed to with fiber. Not talking even about carbon fiber, which is way higher. If you remember the thermogravimetric tests, we do this kind of test, and plant fibers stop at around, degrade at around 300 degrees. So this is a limitation in terms of production, and also in some cases for use, etc. Then there are some specific treatments. For example, maleic anhydride is used a lot for some matrices which are of particular use in, for example, in the automotive industry, because the automotive industry, for example, is very fond about using polypropylene or polyethylene, etc. And therefore, you can make these plant fibers more compatible with polypropylene, polyethylene by using the maleic anhydride. This is called maleianization of fibers. And therefore, in reality, you treat the matrix, you are able to make it more compatible with plant fibers, and to produce also some plates, some semi-finished products, also with more compatible, ensuring more compatibility between the fiber and the fabrics. So this is what happens with, for example, with jute fiber. This is jute fiber, and you can see that it's more irregular than hemp, for example, and it is and here is shown the effect of alkalis of sodium hydroxide together with tension. So you can, it was observed that the effect was enhanced, the effect of regularization obtained by sodium hydroxide was enhanced if you put them also, if you put the fiber also under tension. This is an idea of the work which is done with this kind of fibers. Then you can see the other aspect, which is the fact that internally they are not circular, and also they have some presence of porosity, voids, and so on, which are called lumens. In technical terms, they are called lumens. And they allow the penetration of water, of course. In some cases, they have some particular shapes. These are studies on which we have done some studies, and you can see, for example, okra. Okra is a kind of hibiscus which is typical of Bangladesh, and we didn't have much regularity at all. It was interesting because it was a local fiber which has got some applications, and it is interesting to use it. Also, kind of fibers which are spontaneous, from plants which are spontaneous, have more and more interest for them. Like it is the case for nettle, which has a residual application for textiles, but very limited. And you can use that in composites. For example, Formus is a fiber from New Zealand, although it's also present also here in Italy. It's a kind of not very dissimilar from agave plants, and from the leaves you can take these fibers, which are considerably long. In general terms, the longer the fiber, the more value it has. Apart that, some fibers are in such an abundance, like coir fibers from coconut, that it's worthy to use them as well, even if they are quite short. Some experiments have been done also with waste. We did this with celery waste, and it was around 15 years ago. So it was starting to work on waste from the food industry, and it gives you some results. Although some not all fibers are very appropriate to put them into composites, but it's an attempt which is worth doing, because in any case it might lead in some cases even to industrial products or commodity products and so on. Of course, there are a number of issues, because with glass carbon fibers and basalt fibers, etc., you don't have the problem of mold. You don't have the problem of fungal attack. And also here we have also other problems, is that the seasonality, it's a big problem as well, because, for example, we have something that automotive industry doesn't very much, which is variable availability. You know, the production is done just in time. Production is done just in time, which means that only that only when you need to produce your product, you will have the fibers. In this case, we are talking about fibers. And with plant fibers, this is not possible, because every plant has got its season. So in practice, you may have the fiber only some time during the year. This is it's avoided in the case of some particular fibers like bamboo. For bamboo, you may have periodic cutting during the year, so you cut the plant when you need the fibers. For other fibers, it's not like that. With hemp, you have the two yield over the year, and where you collect the fibers. And in other cases, you just have one. So in practice, this meant that it's not being applied extensively. So you need to have, to simplify the problem, you need to be able to produce textiles. In some cases, you are not able to produce textiles, and your only possibility is to put random fibers. Like, for example, we have done this attempt with celery. With celery, you were just able to put some random fibers, short fibers at random directions into the composite, which improves a little bit the composite with respect to the resin, but you are very limited. If you are able to make this textiles, so if they withstand the and you are able to make the real wires, you make textiles, and then you are able to use them in a higher profile way. Of course, you don't get rid of the properties scattering because it's inherent to the fiber. You can reduce it with treatment and so on, but it's not obvious. Then, how to sell? Of course, everyone has got its fiber and wants to use it. There are some questions also on the adaptability to the application. For example, the fibers may contain more lignin, more cellulose, so they might be more hydrophobic, less hydrophobic. You may be able to use them as substitute for wood. If you require a treatment, and the heavier the treatment, the lower is your environmental profile, because of course if you need to have a more concentrated solution of sodium dioxide to treat the fibers, then in terms of life cycle analysis it's a minus sign. So it is something which needs to be evaluated, starting from the fact that everyone tends to use the fibers at 0 kilometers, so the local fibers. And the other possible applications would always involve the fact that the fiber is anisotropic. You may imagine the anisotropic of the fibers, because also the fibers in bamboo as well, which is one of the best fibers, you have the problems of nodes, because the fibers are built with kind of spruce. So you have basically a nodes, which are larger section parts. Larger section which remove you from cylindrical geometry even more. Then you can have an internal torsion of the fiber. And a big problem is also the fact that you don't have much properties in terms of impact or fatigue. And some have been collected over the years, but still we are very missing of this kind of studies, which are important, for example, for entering the automotive industry and also other industries. Even in the case of furniture and so on, impact might be something which is definitely of interest. So, for example, why one would like to study impact resistance? So basically, impact is a frequent event with the fact that you may have a dropping object which impacts, which hits your material and then possibly even penetrates the material in the case of composites. Of course, even if it's not penetrated, if you have damage, then the mechanical properties are reduced, and you need to consider whether you would like to replace this your piece or not. For example, now they have started making also some fibers, for example, kenaf, which is another kind of hibiscus, is in between the hibiscus, traditional hibiscus like ochre and hemp. And so it is stronger than kind of ochre, but less thick than hemp. So in practice, you can make also some self-foam shells, for example. They have tried to make using polylactic acid, one of the so-called bioplastics, with this kind of kenaf fibers. So there are some commodity applications, some more structural applications. This is a kind of, for example, the use of steel sisal, which is used a lot in Brazil, for example, which is again an agave which is quite spontaneous. It goes spontaneously, and you can make this kind of injection molding. Yeah, because what's interesting is that there are not only disadvantage in cutting the fibers and put them at random. Here the fibers are obviously at random. But if you make them short enough, you can include them into a pellet to make injection molding. So it is interesting in a sense. The worst that you can achieve is that you reduce the amount of plastic you use because you put some fibers, some waste in some cases. So you reduce the cost, you reduce the environmental impact. In some other cases, you can even get to some more tensile strengths, which even in a trivial case like the one of the tray, you need some tensile strengths. So it's important also that with plant fibers, we are able not to go away from traditional way of producing polymers or composites. Injection molding is one. You can also do injection molding in glass fibers. You can have some glass fabrics which are impregnated even by injection molding. Or by lamination and layup, for example, or by other processes like compression molding, inclusion, etc. To try to make them as even and regular as possible, also in terms of thickness and output. So, what is falling weight impact? In practical terms, it's very simple because you get an impactor. The specimen is on the base. What I am not shown here, it's not shown here, but it's obvious is that the specimen needs to be clamped on the base because otherwise it will fall away. Once you impact, it will go away. Or for the effect of displacement induced by the force. And you create from that damage. You can characterize, you can observe under a microscope, for example. And since it's away from a ideal process, you have obviously a kind of hysteresis, which gives you an idea of how much energy from damage is absorbed. So, in detail, impact properties are affected by a number of aspects. Of course, the selection, type of fibers, the extraction, the treatment, this is obvious. If they are compatible with the matrix, how many fibers you put, of course, makes a lot of a difference. Manufacturing, you can put different fibers because in some cases, what happens? Why hybridization? Hybridization complicates your life, and it's clear. In another sense, we can say also that you are not, for example, to substitute all the glass fibers with, for example, hemp fibers. So what you do, you keep some layers with glass fibers and you put some other layers together with hemp fibers. So it's something in between. Possibly because your hemp fiber composite would not be as strong enough to withstand damage. So you can measure the work of fracture. You can have a 1D impact, which we call the IP or isot impact. So basically you kick your sample in one direction, basically, and you measure the work of fracture. You impact the sample in order to break it and to, with an energy which is in excess of the energy which is needed to impact it. But on the other side, you are able to measure the work of fracture. Or you can measure the 2D, so by impacting not with a hammer on one line, but with a weight, an impactor, which is a semi-sphere normally, and a semi-sphere, and therefore you can penetrate it or not, can damage it and damage it up to penetration, so you see damage on the other side, or you don't impact you on purpose. You can impact on different energy, with rising energy. You impact with an energy which is not sufficient to induce penetration, but you measure damage and you measure the residual properties, because, for example, you can impact samples and then you can cut slices, cut the central slice and have a tensile testing, and you can see that the tensile strength will be lower depending on the impact energy you applied, but it's important to know how lower it is and how larger it is the variation of your post impact of your residual property. In materials, when we say material science, when we say residual properties, means properties after damage or after the exposition of temperature or to humidity, etc. So residual, what remains. So this is what happened, for example, with the flux epoxy laminates with different thread. Flux had got a different thread thickness. Well, average, because you can imagine that it's always an average because they are not cylindrical, so it's an average diameter of the thread. And you can have some different kinds of cracking. This is a triangular shaped cracking. This is a reverse pine tree cracking, which is usually called this kind of cracks, which are disposed as the reverse of the pine tree. Or you can have a diffuse cracking with a large thread dimensions. This is, for example, with the hemp. You can have some unidirectional, although you can see that even when it is unidirectional, means then you would like to dispose them in just one direction, but in reality, what happens is that is the same angle plus minus an angle. So there is always a variation. You can see that if they are non-woven, you can have they are not non-woven. You can have some specific features of your damage, and in some cases you can have here is the front and the rear face of the sample. You can have a good, a perfect penetration or not, or you can have a breakage which is in different orientations. For example, here you have a mat, and so the damage is led by the directions of the mat. If you have a perfect penetration, that means that in reality you have a 2D isotropic situation, which is in most cases not the case with plant fibers. You can have some referential orientation of fibers and of strength and of resistance. Therefore, what happens is that you can measure the penetration energy. For example, here was the case with flux, the three-flux epoxy laminate which I have shown you before, and you can have a different penetration energy. So you penetrate them so that the hemisphere goes on the other side. There is a lot of discussion about penetration because in reality you can have penetration, but you can have also showing damage on the other side, back rear damage appearance in practice. Then you have rear damage appearance, which becomes worse and worse, and then leads to penetration. What is really obvious is that the 0.9 flux epoxy, 0.9 diameter of the thread, the flux thread, gives you a larger penetration energy. Then, with respect of glass epoxy of hybrids, it's very far. So you can imagine that impact is still a problem. But if we make a hybrid, in this case, the hybrid was made with 0.9 flux epoxy and glass fibers of 50-50. The properties are closer, much closer than to glass than to the flux epoxy. So it was 2/3 and 1/3. I don't remember well, but it was 2/3, 1/3, and in practice, again, the effect was still reasonable. You could introduce 1/3. Possibly, if you introduce 2/3, then you drop quite at the level, almost at the level of flux epoxy. So, which might be a problem. What you can do, since it is just in joules, expressed just in joules, you can increase the thickness, which might not be acceptable, for example, for the automotive industry. It's not acceptable to increase the thickness above a certain level. Although they have done something by increasing the thickness to use more sustainable materials like flux instead of. This is a typically hybrid. This is flux plus epoxy. This is the hybrid I was talking in the previous slide. And you have the impacted phase. You have the side, and you have damage which progresses and goes till the end, but it's with less evidence. The glass fiber is not able to completely stop damage, and this part, not to say to the core, so you have two skins made of glass epoxy and a core made of flux epoxy. And you have a kind of damage dissipation. The flux core provides some damage dissipation, but not as not sufficient to stop real damage. So this is the experiments which have been done by Mercedes already starting of these samples, 2003, 2004, and later on. They've started using flax and banana, for example, to make these components. This is an old story because already Henry Ford has done these experiments in the 30s using hemp, and he was trying to demonstrate that most components in the old Ford T were able to be produced by hemp. In fact, even the hemp car as a prototype. They have revived this question with flax and banana, and with Curawa, in the case this is Volkswagen. In Brazil, Curawa, it's a local fiber, because, for example, yes, in Brazil, they are not particularly famous for flax. So importing flax to make just in a factory in Brazil some components made of flax might not be the right option. So they have done a number of experiments with Curawa and polypropylene, which is a standard in the components of cars, car components. not the structural components, but the damage taking components, not the components in the cell reserved, but in the other part of the car, which in case of accident can be destroyed to save the passengers. So in this case, the absorption, impact damage absorption becomes very important. So other natural fibers were attempted in the automotive industry, for example, different kinds of jute, um, different kinds of flax, etc. Abaca, which is used usually for tea bags, and it is a close relative to banana, I would say. And this fiber, with respect to banana, it's smaller, it has smaller diameter and is more flexible. So a number of fibers have been used from tentatively from the automotive industry and also from trains. This is a prototype which is with hemp or flax, always hybrids with hemp, partially with hemp or flax. And of course, as the automotive industry has got interest into that, also the building industry has got interest when making panels, plates, etc. There are some other kinds of fibers which can be used. Visible, for example, the studies of ochre and with formin. This is a typical thermogravimetric study, as you can see in formin. And with ochre, you can see the spectroscopy, the Fourier transform infrared spectroscopy with the different peaks, the different peaks for the different substances, which you can different groups, different chemical groups, and basically you can show how evolutes with degradation. This is an example of polylactic formin fiber composite with 40%, up to 40% of formin. You can see that the shape of the fiber is far from cylindrical. With formium, which are leaves fiber, you don't see that much the lumen. There is a lumen, but it's really very small. So the fiber is kind of full, as for section, as a kind of full section. And there are other possibilities which we have talked at the beginning of our presentation, which is the fact that waste. You can introduce, for example, keratin waste from chicken feathers. There have been a lot of studies about wool, about chicken feathers, and this is, for example, a hybrid all with natural fibers with jute and wool, jute externally and wool internally. Here it has been done with jute and waste fiber, waste paper, always in epoxy. The initial studies are always done with in epoxy because it's easy. It's a two-component resin. So basically, you put the hardener and the resin is ready to be used. And it's a possibility to use waste for improved applications. So other possibilities, for example, here with formium and flax. Formium is a type from flax. As for application, it was called the New Zealand flax. In practice, it's called flax just because you can make wires out of it. But the structure is quite similar to flax. As you may observe, it is important that you can, for example, obtain also nanocellulose. You can make more crystalline. If you don't want to use the fibers like they are, you may consider making nanomaterials with the extraction of nanocellulose, in this case with you can compare them with microcellulose and making nanocellulose. These are the electron microscope observations, and you can see the presence of the yielding nanocrystal, which is usually quite low. It's quite low, you get quite low amount of nanocrystal. Apart from that, if you start from microcrystalline cellulose, but they are very pure, and you can make some films also for antibacterial properties and for becoming quite resistant to the action of water and of course the formation of fungi. You can extract nanocellulose also from hemp residues. From waste, it has more sense because since the yield is low, since you get little nanocellulose from your initial fibers, you can think of starting from waste, from pristine end fibers of from carded end fibers, which were waste of production waste, not good for textiles. You can treat them with pectinase in order to remove the glue, the natural glue which is present on hemp, and you can treat them chemically as well with sodium hydroxide. And in the end, what you end, it's this is a typical, you can see that sort of Gaussian curve, that sort of distribution. It's important to evaluate the distribution, the fiber diameter distribution. And this is important as well, because if you want to make a film, of course, you need to have that your span as small as possible to be able to keep your thickness or film thickness. Of course, you insert that. You can make fabric nanocellulose. You can, or you can make them. You can insert them into a matrix, into normally a biomatrix, and so to make these films, which are going to be nanofilms. Also, in this case, it was we stopped at the extraction of microcellulose, which in reality we are microns, and then you try to go from that to nano. You may also suggest that you get only some microfibers, because the dimension of the single filament in, for example, in hemp is in the order of a few tenths of microns, and therefore you can just consider, for example, the very center of these distributions in order to try to extract nanocellulose with higher yield. So I think I'm going to stop here. I don't think I'm saying more than that. I just gave you a vision, a general vision of these properties of natural fiber composites they have. We can use on natural fibers, and I got the work from Francesco about the we presented at the exam. The exam will be not in presence, and I'm going to say the date, which is going to be on for end of June, definitely. To arrange a date the next few days, and discussing also my colleagues of physics to take a commission, and I think that it will be, as I'm saying, after I'll prove your educational paperwork, I will written exam with very general questions, which I suppose will be different for any of you. If you are too few, possibly we'll have just an oral. Depends how many you are really. Anyway, this will be known to you in the next few days. For now, I stop here. Have a nice weekend, and of course, you can email me also to decide what is your subject on which you want to write the educational paper. In a few days, you will have also the date for the exam. Thank you.
Grazie mille, arrivederci.
Arrivederci.